All right, we're going to do another little exciting Bellwork problem here. We've got FG and ST are parallel to each other. First off, which triangles are similar, and then let's solve for x. Okay, well, which triangles are going to be similar here? If I've got this guy parallel, this guy parallel to this guy, that means that my corresponding angles here and here, and I have corresponding angles here and here, making triangle TRS similar to triangle GRF. And if I'm talking in the context from TRS to GRF, would that be a dilation or reduction? We'll quick review there. That would be a reduction. All right, because it's going from big to small. So let's solve for x, shall we? All right, well, I got to make sure that when I set up my proportion that things agree, okay? So let's see here. I've got RG, which is 14. That corresponds to what side of the other triangle? That would be RT, which is 4x plus 11. And then if I took FG, I'd be using 12, and then ST would be 30. Or, and you don't necessarily have to go this far and do this, you could have done our 20 over 50, because I got to make sure that I put the 20 and the 30 together to make sure it's the full side of that triangle, since I'm going full side of the small triangle over the full side of the big triangle, full side of the small over the full side of the big. Okay, so you could use this one or this one paired with this. I am going to pick the middle one here because it's the smaller numbers, and I can also go ahead and just simplify that real quick. Both 30 and 12 are divisible by 6, which would give me 2/5, right? If I were to simplify that, I'd get 2/5 if I divide them both by 6. So now when I cross multiply, I have 14 times 5, which is 70, equals 2 times 4x, which is 8x, and 2 times 11 is 22. Cool? All right, so I've cross-multiplied. Now I need to just solve it. So how about I subtract 22 over to the other side and get 48. And if I divide by 8, I end up with x equals 6. Cool. That was Soup's fun, rad, and cool. All right, so let's dive in a little bit more into congruencies and proportions in similar triangles. Oh, yeah. Let me get 2 new theorems in here, much like we did when we started going with CP/CTC and beyond that. Exciting stuff here, children. Exciting stuff. So just a little recap. What does CP/CTC stand for? Corresponding parts of congruent triangles are congruent. And when can you use it? Once you've proven triangles congruent, right? That's when we can use that. So, same logic applies here. Corresponding sides of similar triangles are proportional. So that one would be proportional. And then corresponding angles of similar triangles are congruent. So this one here we'll abbreviate as CSSTP, and CAS, not a C, TC. We really don't ever use this one down here, mainly because how are we proving triangles similar? Angle-angle similarity. And if 2 angles of a triangle are already congruent, the no choice theorem gives us the third pair of angles congruent. So what the heck is the point of this if we're already at the angle-angle similarity, right? This one up here is the one we will use, and you can abbreviate it as such, CSSTP. All right. So we got some text that seems to have moved on us. This says JM is an altitude. All right. So this angle HJK is a right angle, JM is an altitude, and then we have to prove that JM over MK is equal to HJ over JK. So that's just saying that those sides are proportional, hence the CSSTP. Okay? That's what we're going to be using there. Here's the difficult part, is we need to figure out what triangles to prove similar. We've got 3 triangles here that could potentially be similar to each other. Which ones are going to work for us? So what I like to do is I like to first outline these sides that I have. I want to prove JM, let's see here, MK, and I've also got HJ, and I've got JK. So it looks like to me, and I'm just going to back off on these 2 here and redraw them on. Oops. Let's go with a lovely purple color. This triangle here, since these are the 2 sides, I can make that a triangle right there, and I can make that a triangle right there, the blue guy. Okay? Let's see if we can prove those 2 triangles similar. With that second proportion, the HJ and the JK, that doesn't really leave many options for other triangles. I can't really work with that HMJ because I only have one side that I'm going to be dealing with. So why the heck would I use that little guy? All right, let's see if we can get a couple pairs of angles congruent, shall we? Because remember, our goal is generally angle-angle similarity. That's the one we're going to use most. So it says HJK is a right angle. Let's pop that down. There we go. And then it says that JM is an altitude. And I know if JM is an altitude, then I get perpendicularity. If a perpendicularity, I get right angles. And I know that all right angles are congruent. Okay, so I've got those 2 right angles there. I could prove those congruent. So that's one set of angles there. What else could I do? Well, certainly looks like I could prove angle K congruent to itself. There's my second angle. I can prove these 2 triangles similar. Awesome. Let's go ahead and do that. I am ready to rock and roll with this proof. So I've got given. Let's see here. Let's go with the right angle first. That one's going to be quickest. Or actually, no. Never mind. I take that back. Let's go with the altitude, because if we can get it to be a right angle, we can say they're congruent. Cool. Alrighty. So I have JM is perpendicular to HK. And that would be by definition altitude. And when I have perpendicularity, I have right angles, don't I? So I'm going to call that angle 1. Okay, so angle 1 is a right angle. And I don't really care about the other angle because I'm not going to use JMH, right? And that'd be definition perpendicular. 4th step. I can prove that angle HJK is congruent to angle 1. All right angles congruent. And I can also prove that angle K is congruent to angle K by reflexive. Do I have my 2 angle pairs ready to rock and roll? I certainly do. Let me just move this bad boy up so we can finish this thing out. Okay. Step number 6. Triangles need to be similar. Now, what triangles are going to be similar? How about I just start with the smaller one? Let's go with JMK. It's similar to triangle. Now, what matches up with J? I'm not sure yet. I'm pretty sure, but I'm not totally sure. But I know that K matches up with K, right? Because that was reflexive. Now, my right angle for the first triangle was at M. That was its vertex for M was the right angle. So then J has to be that one here because J is the right angle of the larger triangle. This is the more purpley magenta-y one, right? And then this one is the blue outlined one, okay? And lastly, that's going to be H for this one up here. H is going to correspond to that original J vertex of that triangle. And my reason is angle, angle, similarity. Okay, so last but not least, I've got, let me move this up even a little bit more, I'm running out of room. JM over MK, so JM is to MK is HJ is to JK, LOL. And my reason is corresponding sides of similar triangles are indeed proportional. Woo! That was wonderfully awesome. Okay. Not too bad, right? There's only one other additional thing we're going to do here as far as our theorems with proofs go in this chapter, and that will be next. All right, so what the heck's going on here? It says, well, first off, WZ is parallel to XY, all right? I don't know what the heck happened here, but again, some weird things. Those are just segments or lines. My conclusion, what I want to prove, is that WS times XY is equal to XS times WZ. Basically what we're saying here is when we cross multiply our means extremes product theorem, and you can abbreviate it as such. Okay, means extremes product theorem. That's cross multiplication in the fancy math lingo world. All right, so this is basically the same process as the last one, but one additional step, because once I have the proportion set up, I can cross multiply it. It means extremes product theorem. Let's go for it. So if I got parallel lines, I know that my corresponding, if I'm looking at this particular problem, I know that this guy is congruent to this guy and this guy was congruent to this guy. I'm not as concerned in this one because I only have two triangles I deal with. I know what two triangles I'm going to be dealing with, right? I want to prove triangle. Let's start with SWZ, that smaller one. I want to prove that one is similar to, well, S, X, Y, right? Because Z and Y correspond to each other. X and W correspond to each other, or angles that are congruent. And how do we get those angles congruent again? Parallel lines, corresponding angles are congruent. Cool. We take that all the way back to chapter 5. That guy right there corresponds to that guy. That guy right there corresponds to that guy with our parallel lines. All right, so if I've got my triangle similar, I can set up my proportion and then I can cross multiply it. And that's our CSSTP, and they're mapped. Let's go ahead and write this thing up. That looks terrible. There we go. So, how about we call this angle 1, 2, 3, and 4. So we got angle 1 is congruent to angle 2. Angle 3 is congruent to angle 4. And my reason is, if parallel lines, then corresponding angles are congruent. And for those of you that were like, hey man, what about reflexive property with S? Absolutely could have done that, but that's just going to take an extra step, and an extra step is time, and time is money. That ain't fun, you know what I'm saying? All right, so I've already got my triangles similar, and I've wonderfully written that statement right above, so I can use that. That can be a helpful little thing to do if you're having trouble with any of these proofs, is writing out what you want to prove similar before you even start the proof. And that was angle, angle, similarity. That is a really high up. There we go, it's a little better. All right. Now from that, those two triangles being similar, I can set up that proportion, much like I had as my proof statement last time. Now to set this up, I like to just like uncross multiply it, if you will. So this would be WS, and I want to make sure WS gets multiplied to X, Y. And XS, I want to make sure it gets multiplied to WZ. Make sure they are diagonal from each other, right? That's how the cross multiplication works. And that proportion is from corresponding sides of similar triangles are proportional. So for my last step, my very last stepped, because I'm going to be using MEPT. All right, I've got WS times XY equals XS times WZ. And that would be MEPT. Booyah! Dunzo on that bad boy. Shanana. Yeah. All right, for our last problem here, we're going to do some application of similar triangles. We got Justin Timberlake just purchased a property to build a lake house situated on Timber Lake. And he needs to frame up the gable end walls of the cabin before he can live there as a man of the woods. If the studs are spaced 16 inches on center, how long will the tallest one need to be cut if the roof is a 412 pitch? All right, so some background on the construction aspect of this. All the 16 inches on center means is that we have studs spaced 16 inches, basically 16 inches apart. But what they're really saying is from center to center, like if I drew a line down the center to center, that is 16 inches, okay? But we can basically just think of this as, for the context of our problem, we're going to go 16 inches, 16 inches. Each one of those is 16 inches. That's what that means, all right? And that's a pretty standard thing. If you're building with 2x4s, you go 16 inches apart. All right. There we go. And boom. All right. Now, the other part, it says that it's a 412 pitch. All that refers to is the slope. And we know what slope is. It's rise over run. So 4 over 12, rise over run. And you can think of that as 4 inches for every 12 inches, 4 feet for every 12 feet, 4 whatevers for 4 whatevers, okay? All that means is rise over run. Well, if my rise over run is 4 over 12, this certainly seems like I can set up a proportion of some kind and cross multiply. Well, I don't know how long the tallest one will need to be. I'm looking for this right here, right? That's my tallest one. And the process would be basically the same thing for any one of these, but we're looking at the tallest one here. So that's my rise. Do I know my run, though? Well, absolutely I know my run. It's from here all the way to here, and how many 16-inch sections do we have? We've got 1, 2, 3, 4, 5, 6 16-inch sections that we got going on here, so we have to ask ourselves, well, what's 6 times 16? That's 96 inches. All right. And I think it's helpful to note in an application problem that we're dealing with inches here, right? So inches. Okay, so everything's in inches here. All right. So when I multiply 96 times 4, or wait, hold up. I think I could simplify a little bit first, can't I? I could do, let's see here, what's 12 divided by 4? 3. So I could do 1 over 3. That's what I could do for the 4/12ths, right? So if I simplify that, I just have 1 times 96, which is 96, equals 3 times x, which is 3x. Divide that by 3, and I'm going to get x equals 96 divided by 3, 32 inches. So I'm going to need to cut that stud at 32 inches. All right? Awesome. And once we get even more advanced in our math, get tricky with and all sorts of other things, we can start figuring out what angle that board would need to be cut at as well based off of that slope. It's pretty interesting stuff. But in any event, we could figure out any one of those stud lengths just by the slope of our roof, 412. They always refer to it in something over 12, even though it's not a simplified fraction. And then basically how long we're going, what stud we were at with that 16 on center. Cool stuff. I love it. America, freedom, rock and roll.